Okay, guys, so far we have only studied systems that we define as closed systems. So basically, we were always dealing with these two types of systems. The piston cylinder assembly, okay, or some type of box or container that was closed. So a simple definition, if you want, or characteristic of a closed system is that the mass on a closed system is basically constant. Okay? That's what we had all the time. So now, today, I'm going to introduce the second type of system that we have to deal with, which is, I like to call it in opposite to the closed system and open system. But in textbook, and more specifically in your textbook, they like to call these ones control volume. Control volume systems. And you will see why, okay? They call it control volume. I like to call it open, I like to call it open system just in opposition to the closed system. So this type of system here will be of the form so this is your system here. And the biggest difference between this system here, which is a closed system, is that in this one you will have mass coming in and mass coming out. So basically the mass, I call that m dot, but basically m dot means is the derivative of the mass in function of time. Okay, so I like to call it, again, open system in opposition to this one because you see it's open, but in most textbooks they call it control volume because here you don't control the mass, but what do you control? You control the volume through which there is the change in mass, no? Okay, and generally it helps if you had fluids before coming to this class, but the last 2 years, they changed the curriculum and you take fluids after this class, okay? I don't know if you had a basic class in aerodynamics, but basically in aerodynamics, basically they also use control volume, no? Whatever, so it's the same idea. Okay, so generally, once you come with certain knowledge of fluids, you know what the mass flow is. So before rewriting the first principle of thermodynamics for this type of system, I'm going to have to define some quantities, okay? So the first one is, what is the mass flow? Which is the m dot, which is the m double dot. So basically the mass flow let's say you have a certain opening, a tube that has a certain diameter, and you have a flow going through it at a certain velocity v. So basically the mass flow means what is the amount of mass of that fluid that's going through that opening. Okay, so this is equal to density A times, and here be careful because this V over here is velocity, okay? So if you want m dot equal rho AV, leave some space over here, where here will be rho is the density, A is the area through which the flow is going through, and here V is the velocity. That's why, I don't know if you noticed that in this class, my V's are always doing with a bar in the middle here to differentiate between volume. V with that bar over here is volume. V with nothing is velocity. Okay, and if you remember, what is the specific volume? Specific volume is volume divided by mass, correct? But specific volume, if you think a little bit, is volume divided by mass. That's just the inverse of the density. So the mass flow is also equal to AV divided by little v, where little v will be the specific volume. All right, what else? The quantity AV, so both that quantity together, AV, is known as the volumetric flow rate. Okay, you will find that term in some of the problems. Oh, let's go back over here for 1 second. So what will be the units of M dot, of the mass flow? Will be density is what? Is kilograms, let's say, per cubic meters, no? Area will be the square, and this will be meters per second. I also write here SEC for seconds because the letter S just is reserved to entropy. So at the end, what do you have? The units here will be kilograms per second, which is the amount of mass that's going to go through this area per unit time, no? Okay? So that is what the mass flow is. All right. Do we need anything else? I think we're good. All right. So now I'm going to redo the figure, but using that information, we're going to see what would be the first principle of thermodynamics for an open system. So the first principle of thermodynamics for the closed system was equal to what? Q minus work was equal to change in energy, no? And the mass was constant. In this case, what do you think is going to happen? We're going to have to rewrite this expression, but this expression, instead of being Q, it's probably going to have to be Q dot, because it needs to be per unit time, no? Okay? So we'll see how that ends up. Okay, so somebody asked me, yeah, just call this one mass flow, but if you want to be more specific, this is the mass flow rate, okay? Rate, because it means in function of time. It's a rate. The same thing over here. This is the volumetric flow rate. Specifying this is in function of time, no? Okay? All right, so our goal now is to rewrite the first principle of thermodynamics for an open system or a control volume. All right, so let's over here. For the below open system slash control volume system, so CV stands for control volume. Basically, I just redo the figure. It can be a bit different, but will be the same idea. All right, so this will be our control volume, and we're gonna have mass going in and mass coming out. Okay, so this is our control volume. So over here, before I do the first principle of thermodynamics, I need to specify one thing because you might see it on the textbook. There is something called the conservation of mass in the control volume. So what does that mean? That the amount of quantity going in needs to be equal to the amount of quantity coming out, no? Okay, and let's just call this one m dot. This will be 99% of the problems you'll be solving. Probably I do one problem where it's not the case, okay? But I don't want to overcomplicate the notation. I want you to understand the basics, and I do the complicated case and an exception, okay? All right, so now let us apply in the first principle of thermodynamics to the control volume that I call C dot V with a bar. Okay, so if you remember the general form of the control volume, it always involves, so if we use the textbook notation, what do we have? Heat going in is positive, no? Then you can do the arrows in or out, doesn't matter, but if we use the textbook notation, and then let's say you have work, but this time you see that I put the dot, so this is dq dt, and this is work per unit time, this becomes power, no? All right? Remember, this is the sign convention of the textbook. Okay, so let's say the equation will become what? So we have Q dot minus work dot. But now, so this takes everything comes from the figure. But now you have flow that is going inside the system, no? So plus m dot 1. And the energy inside can come under which form? It can come under, let's say, will be kinetic energy. So this will be equal to what? 1/2 rho v squared can be potential energy rho z. I don't want to use h because h is reserved to enthalpy. Then it can come as internal energy and here, okay, the mass flow can be the same, but if these openings are not exactly the same size, what's going to happen? The pressure is going to be different, no? Does that make sense? So it will be plus some work done by the pressure, that could be plus PV Let's say all this stuff going in, of 1 over here, of 1. Okay, and all this stuff will be equal to what? So we already took into consideration the Q, the power, work per unit time, the M1. Now we need to know what's happening on the exit, no? Okay, so we see will be the same thing here, m dot 2 of 1/2 rho v square rho z plus u plus pv at 2. And now I'm going to add something that, just for the equation to be 100% correct, but that term is going to be 0 99% of the times. All right. Plus, what happens if something happens within the control volume? Okay. So let's say plus dm dt changes in control volume. So this is a general equation. So this is a general form of the first principle of thermodynamics for a control volume. For a control volume or an open system, okay? All right. So, let me simplify that equation. So I will say, in most cases, what do we have? We're going to have dm dt control volume equal to 0, and this will mean we are studying the system at steady state. So basically, at steady state, the amount of mass remains constant. We don't change it right away. We don't change the rate of M1 and M2, no? Okay? What this will say, for example, is that, let's say you have here 1, and then let's say you put a pump over here in addition to this. So then it will change, no? Because you might be removing much mass than you put it in. So something needs to happen, no? Inside, okay? But don't worry, it's just gonna happen once, okay, for you. All right, so this term, 99.9% of the times will be 0, okay? The other one is that in most cases will be neglect, kinetic, and potential energy. So what does that mean? That the 1/2 rho v square plus the density times change in height will also be 0. Okay? And last, it's not going to be an assumption. I need to go back over here. What is U? What is internal energy plus work done by the pressure? What is that quantity? Remember, how do we define that quantity? That was enthalpy. So this is enthalpy. So this is H enthalpy. Okay, so if we do these two assumptions and we simplify the equation, so the equation simplifies to what? Q dot minus power, so heat transfer minus power plus M flow going in H1 will be equal to mass flow. You want to put here M1, M2, H2, but what do we know? We know that M equal M1 equal M2 because of the conservation of mass. So at the end, this will give us heat minus power. So heat transfer minus power equal to M dot H2 minus H1. Okay, so now realize that here now we have the term Q dot. No, so Q dot is heat transfer rate and work dot is what? Work per unit time. So work per time, what is that? Power, no? Yeah? Okay. So be careful, the units change. It's not the same units as Q minus W. So over here, I'm pretty sure most of you are AE. Okay? Some of you might not be AE, okay? So just going to give you, why is this important? If you do aerospace and you do the proportion track, probably you're going to see that H and this type of equation a lot, okay? Because if you think about turbofans, how do they work? So what is the engine of an aircraft, basically of modern aircraft? What do you have over here? The front will be the, this is the inlet. The diameter of the inlet is to control the amount of air going in, no? All right. Now, what is the first thing that you have afterwards? When you look at the aircraft, what is the stuff you see at the front? The fan is so, okay. What is the fan is really what? Is a compressor, okay? So this is the compressor. As its name states, what is the function of the compressor? To compress, no? Okay? So let's say it's an ideal compressor. So what is that doing? It's taking all the air that is coming inside, is going through a bunch of blades, and what it's going to do? It's going to transform. It's going to reduce the velocity, let's say it's the ideal case, to what? To zero, no? But then, if you take zero, what's going to happen? What is the compressor doing? Compressing. So what is going to increase? Pressure becomes much bigger, no? Yeah? Okay. Now, after it passes the compressor, what do you have? You're going to have an area that, if you want, will have a certain control volume. And this is the area where it's going to be, you're going to throw into your system fuel, no? Yeah? So In the ideal case, I mean, it's not happening on the aircraft, but if the pressure is high enough, will you need like a spark to ignite the fuel? No, okay, that's the ramjets. They are based that if you increase the pressure enough, you don't even need a spark. No, all the pressure is going to ignite the fuel itself. But basically what you do over here, you have zero velocity, you move the pressure extremely high, you have a certain volume on the control, and when you throw inside fuel and you light it up, what are you introducing to it? Internal energy, correct? So if you think about it, this is, if you want, the combustion chamber. So really what's happening over here? Here you have a huge amount of what? Pressure times the volume of this area, no? Yeah? So you have work done by the pressure, and what do you do now? You add U. So what is work done by the pressure plus U? What was this? We just said that was equal to the enthalpy, no? Yeah? So between this step and this step, really what have you done? You have created an enormous amount of enthalpy. Okay? Now that you have created all that enthalpy, what do you need to do for the aircraft to fly? You need to transform all that enthalpy into what? Heat for what? Are you cooking? You have to transform it into thrust that is caused by velocity, no? So that the exit velocity is a lot bigger than this one. Okay? So, what mechanical component is doing that? What is at the back? That is related to the front one, because something needs to operate the front one. This is the turbine, no? So now what is the function of the turbine? Is to transform all the enthalpy into what? Into kinetic energy, no? So basically, why am I saying all this stuff? So at the end of the day, when you do the design of an engine, what do you need to do? Basically two things. To make it more powerful, more efficient, you can either increase the pressure, no, which is very important. I mean, there's not much you can do by burning the fuel. Yeah? Okay, it burns, it is what it is. But where can you optimize your engine is by controlling better the pressure, no? Okay, that's why if you look into detail, some aircraft are like single stage compressor, you might have multiple stage compressor, no? But the higher pressure you get, then the lower will be the velocity, the more, so the whole idea behind the design of an engine is to get the enthalpy as high as you can. Okay? Basically just mentioning that. All right, so that's it. Let's do a problem, okay? So let's do 451. For now, let's just copy the figure, and then we see from the problem statement if we need to add some information, okay? All right, but let's do the figure. So problem 451. So let's see, we have a turbine. You don't have to do the correct shape for the turbine. You can do a square and just say it's a turbine. But generally, this is the symbol for the turbine. So basically what you do, instead of compress, you expand. Okay, that's basically the idea. So turbine. So you have flow coming in on one area here. Let me do it here instead of down. And it's going out somewhere over here. They do a shaft because generally there's a shaft connected to a turbine, but we don't really need it. So let's see. we have three, we have one inlet one. This is a shaft, this is not an entrance or anything. So one, then there's another one here. So the flow comes this way, let me do it in red. All right, and leaves through 2 and 3. We have 1, 2, and 3. I have no idea what the substance is, but we'll find out. So we know, what do we know? P1 is equal to 1800 psi, so pound force per inch square. And the initial temperature T1 is 1100 Fahrenheit. They don't give us a mass flow. We know m.2, the mass flow going out, is 0.2, okay, of the mass flow going in. P2 is 600 psi. T2 equal 500 degrees Fahrenheit. And now at 3, we know is saturated vapor, so it's water. We're dealing with water. Saturated vapor. And we know P3 equal to 1 lbf in square. And looks like this heat transfer. So this is giving heat. And obviously this is a turbine, so I'm pretty sure this is providing power, no? Okay? This is what I will understand from that figure. So now let me see the problem statement, see if we can add something. Okay, so steam at 1800 lbf inch square and 1100 degrees Fahrenheit enters a turbine. So something that is not on the figure that we need to put is what? Here we have steam, no? So do we know the state over here? What would be the state if it's steam? Would be vapor gas, no? Okay. And here saturated vapor will be right on the line of the vapor liquid, no? Vapor and mixture. All right, so enters the turbine, operating at steady state. So if it's steady state, remember we have that dm dt equal to 0, no? Okay? We can use the simplified expression. As shown in figure 451, 20% of the entering mass flow is extracted at 600 degrees Fahrenheit and 600 psi, 500 degrees Fahrenheit. The rest of the steam exit on saturated vapor at 1. Okay, so it's obvious, but then we can say what? Here, m.3 will be equal to what? 0.8 m1, no? Yeah, because we need to have the same amount of mass coming in, same amount of mass coming out. So this is m1 here coming in. So same amount of mass should be coming out. If 0.2 is coming out this one, the rest needs to come out through the other one. All right? So let's see. The rest of the team exit as saturated vapor at 1 psi. The turbine develops a power of 6.8 BTUs hours. So this one is 6.8 10 to the 6 BTU hours. Heat transfer from the turbine to the surrounding occurs at 5 10 to the 4 BTU hours. Okay, neglecting kinetic and potential energy, determine the mass flow rate of the steam entering the turbine in pounds per second. So what we need to solve in this problem is we need to solve for this, for the mass flow rate in pounds per second. Okay? All right, so if you want, here I'm going to add some, because of conservation of mass, so conservation of mass. We have mass flow in needs to be equal to mass flow out. No? So in this case, we just say that we rewrote this as m.1 needs to be equal to m.2 plus m.3, and we just say that then m.1 will be equal to what? 0.2 m1. Okay, let's do very detailed, plus m.3, so m.3 will be equal to what? 0.1 m1. We already knew it because you can do it in your head, but since it's the first problem, then let me do all the details. Any question? I mean, I think that's straightforward, no? All right, the next part, be careful because I'm picky about it. We're gonna apply first principle of thermodynamics. So when you say apply anything, to me, you need to let me know to what system. So what will be the system? So this is your control volume. Yeah? I mean, in this problem, it's not an issue because it's only one. But if we look at the textbook, some of the other problems over here, they have how many? They can have 1, 2, or 3, no? So you can have this one can be a control system, this could be one, this could be one, or you could take all of them as one, no? So if you don't let me know which control volume to look at, I'm always going to pick the wrong one. So it's important that you let me know about which control volume you're going to write down the equation. All right. So this is a control volume. So what was the equation we just derived? So we say it's steady state so we knew that the term dm dt control volume is equal to 0. What else do we know? Kinetic and potential energy can be neglected. I mean, you don't need to rewrite this. This is very important to let me know about which control volume. This is not that important, okay? So, what is the form of the first principle that we're going to have to use? We're going to have Q, okay, minus the power plus what? What do we have? Steam entering at what? Here at 1, no? Yeah? And we know the equation was mH over here for the one that was 2. Okay? So this form. So what will you over here? Will be m dot h1, this is coming in, equal to whatever is coming out. So what will you have? M dot h2, and what else is coming out? Plus m dot 3 h3, no? So Q, this is coming in, m dot 1 h1, what is coming out? M dot h2, 2 plus whatever is leaving over here. Okay? So really this is the important equation. If I see that equation, I'm happy. Alright, so now that equation, let me do it here, that way I don't have to write it down and on the next page. What do we know about M2? Will be 0.2 M1. What do we know about M3? will be 0.8 M1, no? So that means that we can rewrite that equation as Q dot minus power plus M dot H1 equal to 0.2 M dot H1 plus 0.8, H2 plus 0.8 M dot 1 H3. So we need to solve for M dot 1. So what do we have? Q minus power okay, plus M dot 1 factor of H1 minus 0.H2 minus 0.H3 equal to 0, or at the end we're going to have that M dot 1, which is what we need to find, will be equal to what? Power minus heat, I'm changing the sign because I'm moving it to the other side, equal to H1 minus 0.2 H2 minus 0.8 H3. Okay, so in this problem, the power and the heat transfer is given to us, no? So what do we need to find? H1, H2, and H3, correct? So from where are we going to get H1, H2, and H3? The tables. So we know what is the substance. So what is the substance? What do I have? 258. Okay, 58, 7. Okay, I will put them in order. The number, I think its number is not good, but doesn't matter. So what do we know about state 1? Let's look at the figure. We need to know, in this one we know multiple things. We know steam, we know the pressure, we know the temperature, no? Okay? So that means that probably we need to go to the vapor, saturated vapor tables in English units. So I know here will be in a silver, this one, so light blue, and it will be table A4E, if I remember right. Okay. So A4E, A3E, properties of superheated water vapor. Okay? All right. I might do another figure. I might do a figure now. What is the pressure? 1,000, no? No, 1,800. So hopefully I have 1,800. Otherwise, I don't want to have to interpolate. No, it's right here. 1,800. And what is the temperature? 1,100, no? So if we look on top, we need H. So H looks like to be is the before last value in BTUs per LB. So from table A4E at 1,800, 1,100, this is equal to 1542.5. Okay? So let's say from table A4E at P equal 1800 and T equal 1100. We have H1 equal to 1542.5 BTUs LB. All right. Okay, so basically, if you had to do the figure, this one of the state, so let's say this will be temperature, okay? TV or T volume, doesn't matter. What is the state one? Somewhere in vapor, no? Okay, and it should be through a line of 1800. So, what do we know about state 2 or state 3? Let's go to state 3 first. What do we know? Is saturated vapor, no? So what does that mean? It's probably going to be somewhere very low on the curve over here, no? So it should be 2, and this one will be going through a line here, very small line of P3 equal 1 LBF. So what about we do, 3. This is 3, not 2. 3, no? So let's go for 3 first, okay? Doesn't matter, we can do probably 2 as well. So H2, we know the pressure, and we know this is the saturated, no? Okay? So we can probably get that value from 2 tables, but I guess the best one will be to go to table A3E. Could we get it from this one? Maybe, I don't know. What is it? 1 LBF. I know we have one for 1 LBF. We can get it from this one as well, if we have 1 LBF. We have 1 LBF here. So we know we are along this line, no? Yeah, which is the saturation temperature. So if you want, and this is 1 LBF, we are looking here for the value of G, no? This is liquid, this is gas, no? All right, so we go to the tables. What is the H? Should be here, 1105.8. Okay, but from where could you get it as well? Let's say we go over here to table A3E. What is the pressure at 3? Is 1. So do we have 1 over here? 1. All right, we need to look at what? H sub G, no? What is the value we have? The same one, no? Which is a good thing, no? So which one you want to use? A3E or A4E? I mean, it doesn't matter, no? Let's say A4E, so I'm going to write table A4E at P equals 600, no, P equal 1, and we know at state, saturated vapor state, we have H3 equal to 1105.8 BTULB. I'll show you right now what I wrote, okay, on my paper. So you need 2 things. 1, the pressure, and the other thing we know is what? We know the state is saturated gas or saturated vapor. Okay, saturated gas. So we know it's going to be right over here, right on the point on the curve. Okay, now what about H2? So we don't know the state of H2. So what do we know for state 2? For state 2, they give us that P2 is equal to 600 and T2 is equal to 500 Fahrenheit. Okay? How can we find the state? We could maybe go to table A3E, which I guess is not this one. I mean, we could also go to this one, doesn't matter. We could do with A2E. No. We could go to A2E as well, but let's go to A3. For the pressures, we have, what is the pressure? 600. So we have 600. What is the saturation temperature? 486.33. What is the temperature we have? 500. So what is the state? It will be gas, no, or vapor. Yeah? Because if we go and look at this figure here, if we go through a line here of 600, that temperature here will be the, whatever, 483 was the saturation temperature, no? And ours will be the highest, so it will be somewhere over here. I have no idea where on the line, but let's say it will be here. Okay, I don't know what it would be, but we know the state will be over there. So now that we know what is the state, so let's say T2 higher to T saturation that we say was equal to what? 486.33 from table A3E. So now that we know it's going to be vapor, what is the table we need to go? Table A4E, no? Okay, so we go to table A4E, add two things. We need to know two things. So we know the pressure, 600, and T equal 500. We're going to get from here H2. So here we go, A3, page down, A4, 600. Oops, here we go. 600 and temperature 500. So it's the first one here. So we'll have 1216.2. So we have that value, so we got all the data that we need now. So we can just go to the top equation. We might have to be careful with the, okay, see what happens with the sign. So substituting into m.1 equal to power minus heat transfer divided by H1 minus 0.H2 minus 0.8 H3. So all right, I don't like the notation of the book because now I'm going to have to put positive or negative. So, okay, so let's see. Hold on 1 second. The units. So let us first look at the units, all right? See what's happening with the units over here. So what would be the units on top? Should be, for what they give us, BTUs hours, no? Yep. We're going to have BTUs per hour. And at the bottom, we're going to have what? BTUs per pound, no? Okay? So the BTUs will cancel out. So really, this is giving us pound per hours, but they're asking us to solve the mass flow rate in pounds per second. Okay? So let's do it in pounds per hour, and then we transform it into pounds per second. Is that okay? All right. So at least we know what we go over here. Okay. So m.1, let me just rewrite it, equal to okay, so here, again, I'm not a big fan of the textbook notation, but I have to deal with it. What is the textbook notation? Is heat going in is positive, heat coming out is negative. Work coming out is positive, work coming in is negative. Okay, that's the textbook notation, no? So in this case, what do we have in this problem? Just trying to look at the values. So will the Q be positive or negative? Should be negative, no? So we're gonna have this one minus this one should become positive. So it looks like this is gonna be equal to, so the work is coming out, so that one remains positive, is 6.8 10 to the 6. But then we're gonna have minus 5 10 to the 4, and all the top would be in units of BTUs hour, and then at the bottom we have H1 that was equal to 1542.5 minus 0.2 times H2, that is 1216.2, minus 0.8 H3, which is 1105.8. And this one was in BTUs LB. So please do that calculation and give me the result in BTUs LB, in LB hours. So somebody gave me the result to be 16,521. We need to remove 1 hour. So in 1 hour you have 3,600 seconds. And this gives us that M1 is approximately equal to 4.59 pounds per second. All right, guys, so please practice using the tables, because this type of problem we just did now, we're going to be doing that over and over and over until the end of the semester. And every time a little bit more complex. So like, again, just in this chapter here that we look at it, what was chapter 4? What am I here? So chapter 3. Okay, as we say here, will be more and more this type, okay? So we'll be over and over using the tables. You see over here, all this stuff will have to come from the table. So practice, because it's going to pay off. All right, so have a nice weekend, guys.